AP Calc 5.2, day number 2, as well as a little bit of 5.7. Just to note, all the problems that I'm going to do in this video are directly from the homework packet. Now our goals are simply to do the following: to be able to use Riemann sums left, right, midpoint, and trap with numerical data from tables as well as graphs, and analyze the difference between distance and displacement. So, all right, let's get started with example 1 from 2003, homework packet, page 16. The rate of fuel consumption in gallons per minute recorded during an airplane flight is given by the twice differentiable and strictly increasing function r of time t. The graph of r and the table of selected values of r of t for the time interval from 0 to 90 minutes are shown above. Part C of this particular problem says approximate the value of the integral from 0 to 90 of r of t using a left Riemann sum with 5 subintervals using the indicated data. Is this numerical approximation less than the value of the integral from 0 to 90 of r of t? Explain your reasoning. Okay, so let's get into a little bit of calculation here. So we are going to approximate the integral from 0 to 90 of r of t using a left Riemann or rectangular approximation. Okay, so I'm going to take my first interval. Okay, the base of that first interval will be 30 minus 0. And using the left Riemann approximation, or rectangular approximation, we're going to take r of 0, which will be 20, okay, plus the second interval from 30 to 40, which if I took 40 minus 30, I'd get 10. That's the base length of that rectangle. Okay, using the left rectangular method, r of 30 will be 30. We'll calculate that in just a moment. The third rectangle from 40 to 50, 50 minus 40 is 10, times r of 40, which is, of course, 40. We'll get to that again in a moment. The fourth rectangle from 50 to 70 will have a base length of 20 times r of 50. Looks like we might, I don't know if this is, I believe this is going to be non-calculator. So we'll get to that in just a moment. And of course, our fifth rectangle from 70 to 90, base length of 20 as well, times r of 70. Okay, let's put our numbers out here. That'll be 30 times 20 plus 10 times 30 plus 10 times 40 plus 20 times 55 plus 20 times 65. I'm going to go ahead and get my calculator out here. I'll be right back. So according to my calculations, I get 13,600. This would be gallons. Okay, so we're going to have an approximation here. Now, let's go ahead and sketch our rectangles. Okay, so our first rectangle from 0 to 30 would look like such. Our second rectangle from 30 to 40, like this. Third rectangle from 40 to 50. Of course, this is using, like we had mentioned, the left rectangular approximation method. From 50 to 70, and from 70 to 90. Okay, now we can see clearly, based on this sketch, that our approximation, okay, So our LRAM is going to be, our numerical approximation will be less than the actual. So yes, our numerical approximation will be less than the actual from 0 to 90 of R of t. And this is because, should add this, R of t is increasing over that interval. All right, let's do another example. All right, 1999, page 17 in your homework packet. We're given a table of values. The rate at which water flows out of a pipe in gallons per hour is given by a differentiable function r of time t. The table above shows the rate as measured every 3 hours for a 24-hour period. Use a midpoint sum, or Riemann sum, with 4 subdivisions of equal length to approximate the integral from 0 to 24 of r of t dt. Using correct units, explain the meaning of your answer in terms of water flow. Okay, so let's go ahead in part A. Now we got to do a little bit of work here to set this up. So let's take a look. We want how many subintervals? It looks like they said 4 subdivisions. So I'm going to go from 0 to 6, 6 to 12, 12 to 18, and finally 18 to 24. Now, when I use a midpoint rectangular approximation, the midpoint is going to be, like I said, the middle of each of those intervals. So typically they set it up so it works out nicely for you. Okay, so this is going to be approximately equal to, this will be for the red rectangle, it'll be 6 minus 0 times r of 3. Right, which is clearly the average of 6 and 0. Okay, I'm going to do the same thing, 2, 3, and we'll hammer out all those details right here. So let's go 12 minus 6 times r of 9, 18 minus 12 times r of 15, and finally 24 minus 18 times r of 21. Okay, so for our red rectangle, we have a base length of 6 and a height of 10.4. This is clearly a calculator, I believe a calculator allowed question. We'll see. Maybe the math comes out to be easy. We should have labeled it. Okay, each of the subdivisions are going to be the same width. R of 9 here is 11.2. Okay, 6 for the width, and r of 15, which is 11.3. And finally, 6 again for the width, and r of 21, which is 10.2. Okay, so the integral from 0 to 24 is going to be approximately equal to, I'll come back with some numbers here. Okay, so to make my, just FYI, to make my calculation a little easier, since each of the subdivisions were the same, I just took 6, factored it out, and then added 10.4, 11.2, 11.3, and 10.2 together. Okay, so you can kind of see my algebraic steps here. And 10.2, and it came out with an answer of 258.6. Now let's talk about the context of the problem. The rate at which water flows out of the pipe in gallons per hour. Now when we integrate, this would be the total number of gallons that came out of the pipe. So this would be our answer in gallons. So how we could describe this is from t equals 0 to t equals 24, 258.6 gallons have left the pipe. Okay, during that 24-hour period. Okay, now of course this is an approximation of the number of gallons, but we can work with that. Okay, part B. Is there some time between 0 and 4 such that r prime of t equals 0? Justify your answer. Okay, so this to me screams mean value theorem. Okay, so mean value theorem, right? I would have to kind of go through a 3-point checklist, right? I have to be able to say, is r of t continuous on the interval from 0 to 24 and differentiable on the interval from 0 to 24 non-inclusive, right, or open. And I can say yes, right? I can say yes it is. As I look at this, it tells me that r is differentiable, right? And it doesn't really refer to any sort of domain, but I'm going to make the assumption that r is differentiable for this entire interval and potentially even beyond, okay, but for sure for this entire interval. And we know that if a function is differentiable, then it is definitely continuous on that same interval. So we can go check and check. The second thing we want to do is we want to find the slope of the secant line. So the mean value theorem tells us that r prime at some value, right, some value t, has to be equal to, if the function is differentiable and continuous on this interval, it has to at some point be equal to r of 24 minus r of 0 over 24 minus 0. What does that mean? That means that the slope of the tangent line somewhere in the curve has to be equal to the slope of the secant line. So I'm going to do a little bit of work here. That tells me that r prime at t has to be equal to, what would that be, 9.6 minus 9.6 over 24, which means it has to equal 0 somewhere. Thus, in kind of the third step of that checklist, so to speak, you could say, therefore, by the mean value theorem, and I'm really just restating the question, there is a time, or there exists a time t, lowercase t, yep, where t is between 0 and 24, such that, that's not one word, but apparently I made it one, r prime at t equals 0. All right, anytime I see, is there a time, on this interval, and then I see r prime, if I'm given the information for r of t, that means mean value theorem every time. Okay, all right, let's move on to another example. Okay, 2015, this is on page 14 of your homework packet. Johanna jogs along a straight path. For the interval from 0 to 40, Johanna's velocity is given by a differentiable function v. Selected values of v of t, where t is measured in minutes and v of t is in meters per minute, are given. Using correct units, explain the meaning of the definite integral from 0 to 40 of the absolute value of v of t in the context of the problem. Approximate the value of v of t, of the integral from 0 to 40 of the absolute value of v of t, using a right-Riemann sum with 4 subintervals indicated in the table. Okay, so let's just kind of look at the situation here and kind of determine what's going on in this jog. Okay, so here she is. She's just starting. She takes off. Okay, 12 minutes later, she's traveling at 200, meters per minute. Okay, and then, hey, speeding up a little bit. It kind of catches the wind there a little bit or something. Got a tailwind. But then at time t equals 24 minutes, what's going on here? Well, a negative velocity means that she's traveling in the opposite direction. So let's say she was traveling east for some time, up to some time between 20 and 24 minutes, and then she turns around for whatever reason, whether she wants to head home or whatever the situation might be. Okay, and then somewhere between 24 and 40, she turns around again and heads in the same direction she was from 0 to 20 something in here. Okay, now I'm not quite sure. Maybe she was running to school, forgot something at home, so she turned around and then starts running back to school. I don't know. We don't know the scenario. That's basically what this is telling us. It's telling us a story. So using correct units, explain the meaning of this. So the absolute value brings some meaning in. Right? We don't know the distance from home to school, but we know it's going to be longer than her current jog, right? Because she went one direction, turned around, went the other direction for a certain period of time, which we're unaware of, and then she turned around and went the other direction. So when we talk about the absolute value of v of t, if she jogs for 40 minutes, the absolute value of v of t and the integral therein of 0 to 40 indicates the total distance traveled on the jog. And that, of course, in this case will be in meters. Now, this can be different than the integral from 0 to 40 of v of t, which we will have a little discussion about down here. Okay, so approximate the value of this integral. All right, let's go ahead and do that. So let me move this over here. And go 0 to 40, absolute value of v of t, dt. All right, so let's see how far Johanna jogged. All right, first interval or subinterval. Of course, what are we using here? A right Riemann sum. Okay, so I'm going to take 200 minus 0 times v of, oops, I flipped that around. Okay, let's get this straight. This is 12 minus 0. This happens on occasion based on how they orient the table, times v of 12. Okay, so don't fall into that trap like I just did. Okay, then we're going to go from 12 to 20, so that's 20 minus 12 times v of 20. Right, we're doing a right Riemann sum. Okay, third interval, 20 to 24. 24 minus 20 with a 4 times v of 24. And actually, I should be really careful here. This is the absolute value of each of these velocities, which only changes the velocity of the third interval. And then plus 40 minus 24 times the absolute value of the velocity at 40. Okay, so really what are these? These are time times speed, which is going to give us distance. Remember, speed times time equals distance. Okay, and we do that for each of the intervals. So time, speed, and etc. Okay, so let's make a calculation. So 12 minus 0 is 12 times the velocity at 12, which is 200, plus 12 minus 20 minus 12, which is 8. Get your words. Absolute value of the velocity at 20 is still 240. Plus 24 minus 20, which is 4. Absolute value of the velocity at 24 will be positive 220. And finally, our last interval, that'll be a 16 times the velocity at 40, which is 150. I'm going to do a calculation off camera, and then we'll talk about units. All right, it looks like I come up with 7,600 meters. Okay, so an extension on this, right? Says to find the integral from 0 to 40 of v of t dt. What is the meaning of this integral? So let's say we had worked with what we had up here. Of course, our third term would be negative, right? So our value would be less than 7,600. It'd actually be, what would that be, 880 less than 7,600. So we would take this minus 880, and really what does that represent? Well, if we think of this as distance traveled, right? She's traveling to the right, and then all of a sudden turns around, goes to the left, and then travels to the right, right? Well, let's say this is home, and this is school, kind of this finish line, so to speak. Right, so if we travel along with her and we take the absolute value of velocity, we found the total distance she traveled by foot. But if we just find the distance from home to school, that's called the displacement. Right, the displacement, which is the actual distance between start finish, not including any mishaps in direction. Okay, so this is displacement, whereas absolute value is total distance. All right, let's look at another example. Okay, 1998, page 19 in your homework packet. Let's get it started. Number 85, this would be a calculator aloud question. Let's go ahead and read and see how much we actually need that. A function f is continuous on a closed interval from 2 to 8. It has values that are given in the table above. Using the subintervals 2 to 5, 5 to 7, and 7 to 8, what is the trapezoidal approximation of the integral from 2 to 8 of f of x? Okay, so let's write this down. 2 to 8, f of x, dx. Okay, and let's recall the area of a trapezoid. Okay, so the area of a trap is going to be 1/2 base 1 plus base 2 times the height. Okay, so let's identify the heights first. The heights are actually the interval widths. So here I have a height of 3, and we'll go with a blue for the first interval. Here I'm going to have a height of 2, and here I'll have a height of 1. All right, so that's your interval width. Okay, and then our two bases, right, are going to be the outputs of the endpoints of those intervals. Okay, so we'll see as we build it here. Okay, so we're going to have, I'm actually going to, let me lay this out simply here. Okay, I'm going to have 1/2 due to the fact that I'm going to use this formula 3 times. I'm going to actually factor out a 1/2. Okay, and I'm going to build each of the base 1 plus base 2 times heights along the way. Okay, so my height is going to be 5 minus 2 for the first trapezoid, right? Distance between the bases, and we can build this visually here as well. I'll actually do that to try to keep it simple. All right, so here's x f of x. Not to scale, don't judge. All right, so I got 210. And I got 530. And I got 740. And I got 820. Yeah, it's not perfect, but we can work with it. Okay, so I got a trap from 2 to 5. Okay, so the output for 2 is 10. The output for 5 is 30. There's my trap. Okay, you can see I got 2 right angles right there. Perfect. Okay. Then let's go from 5 to 7. Okay, so 5 right here, up to 7, which is at 40. Boom, there we go. And then from 7 to 8. And that goes down to 20 at 8. All right, definitely not to scale, but that's okay. We can visually imagine this. Okay, so I don't know what f of x looks like, but it looks, something like that maybe. I don't know. Whatever. Doesn't matter. Regardless. Okay, so here is our first height. And then we got our second height. And we got our third height. Okay, so you can kind of visualize that. All right, so let's build this. And I'm pulling the 1/2 out to try to keep this, well, actually just to try to show you a new method, so to speak. But you kind of already know that a little bit. I alluded to it in earlier content, so let's build this thing. Okay, so blue, we got 2 outputs. We got f of 2 plus f of 5 times 5 minus 2. For the green, I've got f of 5 plus f of 7, 7 minus 5. Purple, f of 7 plus f of 8, 8 minus 7. Okay, I went overboard there with my detail, but I need you to kind of get the process. Okay, f of 2 plus f of 5. That's 10 plus 30, which will be 40 times 3 plus, okay, of course that's a portion. That's not the area of that trapezoid. That's a portion of the area because the 1/2's been factored out. Okay, and then I've got f of 5 plus f of 7, which will be 70. And that'll be multiplied by 2. That is a portion of the area of the green trapezoid. And then for the purple, f of 7 plus f of 8, which is 60, times 1. Okay, I'm going to take half of that sum. That'll be 1/2 of, what would that be, 120 plus 140 plus 60, which will be half of 260, 320. Yeah, 320. Okay, so the integral from 2 to 8 of f of x dx is approximately equal to 160. Looks like C. All right, let's move on to the next question. All right, last question for our notes today, 2006, Form B, in your packet, page number 22. Car travels on a straight track. During the time interval from 0 to 60, the car's velocity measured in feet per second and an acceleration of a measured in feet per second are continuous functions. The table above shows selected values of these functions. Using appropriate units, explain the meaning of the integral from 30 to 60 of the absolute value of v of t in terms of the car's motion, and then approximate it using a trapezoidal approximation with 3 subintervals determined by the table. Okay, so as we talked about earlier, the integral from 30 to 60 of the absolute value of phi of t represents, I'm going to write it as reps, the total distance in, oh gosh, what does that be? Feet. Traveled by the car during the 30-second interval. 30-second interval. Okay. All right, so let's build this and make our calculation. All right, so the integral from 30 to 60 of the absolute value of v of t. Let's set up our intervals. So we're going to go from 30 to 60, 3 intervals. That'll be interval 1 interval 2, interval 3. I'm going to kind of skip to it and do some of this work a little bit more briefly and work the brevity of it. Okay, so we don't need acceleration in this problem. It was probably part of part B or C or whatever the original question was. So let's go ahead and build this. All right, since this is trapezoidal, I'm going to pull out a half. And for each, I'm going to find my two bases, add them, multiply by the height for each of those three. Okay, so I feel like I've set it up pretty well up to this point in the previous examples, so you know where everything's coming from. So let's talk this through. Okay, so for this first interval, the width of the interval is 5, right? 35 minus 30. The absolute value of v of 30, right? Absolute value v of 30, right, is going to be the absolute value of negative 14, which would be 14. Absolute value of v of 35 is going to be positive 10. Now that absolute value of v of 35 is going to show up again in the next interval. All right, the next interval has a width of 15. The absolute value of v of 35 is 10. Absolute value of v of 50 is 0. Our third interval has a width of 10. And we get 0 and 10. So calculations are relatively easy here, but we can go ahead and lay them out. Okay, 24 times 5, that's 120. Okay, 10 times 15 is 150. And 10 times 10 is 100. Okay, so we get that the total distance traveled by the vehicle, would that be 370? 370, half of 370, I believe, is 185 feet. 185 total feet traveled by the car from t equals 30 to t equals 60. All right, guys, that is it for today. We will see you in the next video. Have a great day.